Hello, this is Brian Washburn. I'd like to talk about today generalized momenta, generalized force, and the concept of a cyclic coordinate. So what we're going to do is, using our Lagrangian formalism, we're going to define a generalized force and generalized momentum. So these are the definitions. So what I'm going to define is a generalized force, PQ, as the partial of L with respect to Q dot. And then I'm going to define a generalized force as the F sub Q as a partial L with respect to Q dot. Okay. Now, again, what I'm going to do is I'm going to make these definitions and then show that these generalized momentum and forces are equal to real forces and real momentum. Now, just to make it very specific, just to remind yourself that the Lagrangian in general is going to be a function of my generalized coordinate, my generalized velocity, and time. Okay. Now you may say, well, what is a generalized momentum? Okay, well, a generalized momentum is just something that looks like a momentum in the Lagrangian system. Now, in reality, that generalized momentum, P sub q, may be a couple things. It may be for a particular problem. It depends on the problem. So it may be a linear momentum, or it may be an angular momentum. It just depends on the problem. Okay. Or it might be something fictitious that looks like a momentum. Okay. Likewise, if forces, we're going to have generalized forces. My generalized forces, again, for a specific problem, may be a real force, or maybe a torque. Again, and we're going to see these things in specific problems. Now, what I'm going to do here is I'm going to look at a one-dimensional case and show that the generalized momentum is equal to a linear momentum and a generalized force is equal to a real force. So let's take a look at a one-dimensional problem. Now, in my problem, what I'm going to have is I have a particle, a mass m, that just moves along one dimension, and we'll call that one dimension x, where x is really the Cartesian coordinate x. That particle can have a kinetic energy. The kinetic energy is equal to 1/2 mx dot squared. So another way of saying is that the kinetic energy is just going to be a function of x dot by itself, not a function of position. The potential energy, well, it could be spring potential, it could be gravity, but the potential energy, if it's conserved, is always going to be a function of just x by itself, not x dot, because if it was a function of x dot, it'd be non-conservative. Okay, so my Lagrangian, if you take a look at my Lagrangian is going to be equal to t, which is a function of x dot, minus u, which is a function of x. Now, let's take a look at those definitions. So let's take a look at the partial L respect to x. Okay, well, yeah, let's do x. Okay, so if you take a look at that, now notice the only thing that has an x is u. So that's going to give me minus the partial of u respect to x. But that is equal to a real force. Okay, because remember my definition, I have this relationship, minus partial the gradient of u is equal to a force. We saw that before. And so then here I show this, that definition of a generalized force is equal to a real force in this direction, f in the x direction. What about the other derivative? The partial of L respect to x dot. Okay, if you take a look at that, that is going to be equal to the partial of t because of respect to x dot. Okay. So that's partial x dot of 1/2 m x dot. That's going to give me equal to mx dot. Okay, but that's p. That is the linear momentum. So we showed here in this one-dimensional conservative case that the generalized force is equal to the real force in a particle, and the generalized momentum is equal to the linear momentum of the system. Okay. Now let's take those terms and put them back into the Lagrange equation. Now remember what the Lagrange equation told me this, that partial L respect to x minus d dt of partial L respect to x dot. Okay. So equals 0. So let's put those terms into there, and we're going to get here, I'm going to get f of x minus, sorry, that's a minus sign there, minus d dt of px equals 0. Well, what is that equation there? That equation says f of x is equal to px dot. And that's Newton's second law. Okay, so we showed, first of all, that these generalized momenta and these generalized forces for a one-dimensional case gives us the real force and the real linear momentum. Plus, if we stick that back into the Lagrange equation, we get Newton's second law. That's cool because that's what we want. We want to make sure that our Lagrangian formalization gives us the same results as Newton's law. In fact, what this does is this shows, remember in using Hamilton's principle, that shows that, Hamilton's principle says that the action integral of the Lagrangian, which is the kinetic energy minus the potential energy, is minimized. The question was, why is that Lagrangian, which is the kinetic energy minus potential energy, why is that a quantity of interest? The reason why it's a quantity of interest is because if we had any other quantity, Lagrangian mechanics would not give me the same results as Newton's laws. So I have to, that thing that's minimized, that thing that's in the action integral has to be the kinetic energy minus the potential energy. Because if it wasn't, then Lagrangian mechanics would not be equivalent to Newton's laws. Okay, that's really important. The final thing I want to talk about is this idea of a cyclic coordinate. So notice that the Lagrangian is a function of, in general, is a function of L, L dot, and T. Okay, for conserved functions, conserved systems, it's just going to be a function of, L is going to be a function of Q and Q dot. Now, if say the Lagrangian is not a function of a specific generalized coordinate, call it Q. Okay, that means that the partial derivative of L with respect to Q is equal to 0. So back to the Euler-Lagrange equation, that means that the complete derivative ddt of partial L with respect to Q dot, okay, is also equal to 0. However, this thing here, this partial L with respect to Q dot, that is a generalized momentum. Okay, so if the Lagrangian is not a function of Q, that means that P sub Q, which is a generalized momentum for the variable Q, is constant. So that means that whatever this quantity is, it's a conserved quantity. So that's really neat, because then what we can do is, if we want to identify conserved quantities, we just look at the functionality of the Lagrangian. If the Lagrangian is not a function of Q, all right, there's no Q in the Lagrangian, now what that means is that the generalized momentum associated with Q is a conserved quantity. And that's a real powerful feature of Lagrangian mechanics. You can just look at the Lagrangian. You don't even have to get the equations of motion. You don't have to solve the equations of motion. You just have to look at the functional form of Lagrangian to identify conserved quantities. Okay. Now that quantity, that Q, that variable Q, is called, and has two names. It's called an ignorable coordinate, or a better term is called a cyclic coordinate. Okay. Ignorable means, it sounds like you just ignore it, but really it's important because you can't ignore it because it's conserved quantity. You don't want to ignore that. So I like the term cyclic. Okay, and so that, and the main thing I have kind of written here, so we can, you can just look at the functional form of the Lagrangian to get conserved quantities. Now that's pretty heavy. All right, so I think it's best to look at this in terms of a problem. Okay, so let's do that. So I'm going to start this problem, and I'm going to finish this problem in a different video. But let's take a look at this particular problem, and I'm going to show you how we can use this concept of cyclic coordinates. Okay, so the problem is this. I have two masses. Two masses are attached to a spring, and I have a table. I have a frictionless tabletop like this, and there's a hole in the middle. And the one mass that's on top of the table has mass m, little m. And then a larger mass hangs, or a different mass hangs on underneath the table, and then this thing can rotate and it can change its distance rho from the hole. Okay, so if we look, so we're going to want to solve for all possible motions for mass little m and big M. Okay, so let's first write down the equations of constraint for this particular problem, and then we're going to look at the Lagrangian. Okay. So what constraints do I have? Well, first constraint is that mass little m can only move on the surface of the table. It cannot lift up. It can't come off the table. Okay, so basically it moves in xy plane. The error constraint is that there's a string of length little l that attaches mass little m to big M. So that distance, so what is L is the length of the string. Rho is the distance that the little mass is from the hole to where it is. And then Z is the distance that big mass, or the big M mass, hangs below. And so that means that the sum of rho plus Z has to equal the length of the string. So that's equation 2. And then finally, mass M, we assume that it can move in the Z direction, moves up and down. So a natural coordinate system for this is just cylindrical coordinate system. Mass little m, this moves into plane. So the kinetic energy of this guy is just going to be equal to 1/2 mv squared. Okay. Now, so remember, there's two particles in this particular problem. So the little mass has a kinetic energy with the fact that it's moving in xy plane, and then the big mass, or big M mass, moves up and down. So this term here is the kinetic energy associated with mass little m, has a radial and a tangential component. And then this guy here is the kinetic energy associated with the big mass going up and down, 1/2 mv squared. Now what about potential energy? Take a look at potential energy. Potential energy we're going to define as a plane of zero energy here. And so then this mass here, little m, has zero potential energy. However, the big mass, it hangs the distance z down, so its gravitational potential energy is m minus big M gz, where z is the distance below. So that gives me my Lagrangian, which I show here. Now, take a look. There's two variables. This is a two-dimensional motion problem. My two variables are both phi and rho. However, look, if you look at the functional form of the Lagrangian, okay, does it have a phi in it? Okay, yes, phi is here. Okay, so phi is not, sorry, let's take a look. Sorry, I said rho. Okay, take a look at rho. All right, is there a rho in here? Yes, there's a rho and a rho dot. Okay, so rho is not a cyclic variable. Let's take a look at phi. Is there a phi in this equation here? Well, there's a phi dot, but not a phi. That means that my Lagrangian here, so that means that the Lagrangian, just writing it, is a function of rho, rho dot, and phi dot, but not phi. So that means that phi is going to be a cyclic variable. And so that means that the generalized momentum associated with phi, which I'm going to call rho, p sub phi, okay, this is going to be equal to a constant. Now let's take a look physically. What is that thing? All right, let's do that next slide. So again, I rewrote my Lagrangian, and my Lagrangian is a function of rho dot, rho, and phi dot, but my Lagrangian is not a function of phi. That means that phi is a cyclic or ignorable variable. Now that means that the partial L respect to phi dot is equal to a constant. Okay, you may even say, well, why is that? Okay, remember, if I write down the Lagrange equation in general for phi, I say this, okay, and then ddt of this, okay. Because there's no functionality, since the Lagrangian is not an explicit function of phi, this is equal to 0. That means that ddt of partial L respect to phi dot, but that's equal to ddt of rho sub phi is equal to 0. That means that p sub phi, that generalized momentum, is equal to a constant. Physically, what is that constant? All right, well, let's just calculate it. So p of phi, okay, I can take partial L respect to phi dot. That's its definition. That's just going to look at this term there. So I get a 2, so I'm taking just the partial of that respect to phi dot. That's going to give me 1/2 m rho squared phi dot times 2. The 2's are going to cancel out, and then I'm going to get mass times rho squared to the phi dot. Now what I'm going to do is I'm going to separate that rho dot, and I'm going to get rho squared, m rho times rho this. Now this thing here, that's the tangential component of the velocity, or the tangential speed. That's that's m rho v tan. Well, back to what we learned in engineering physics, that is the angular momentum associated with the thing moving in a circle. So this thing here is a conserved quantity. What that means is if rho gets smaller, then phi dot must get larger, and vice versa. Okay, so that's the cool thing about Lagrangian mechanics, is that we can, without solving any equations of motion, we can get conserved quantities just by looking at the functionality of the system. Now, before I end, let's think about why angular momentum is conserved. Okay, you think about this guy moving in a circle. Okay, you ask yourself, are there any forces acting on it? Yes, there's the tension. The tension in the string that acts on the mass. Okay, remember, we're talking about the angular momentum of the little mass, m. Okay, is it conserved? Yes. So yes, to answer that question, you think, is there any forces acting on little m? Yes, there's a tension. Okay. Does that force create a torque? The answer is no, because the direction of that tension is along the radius of that circle. So even though there's a net force acting on it, there's no net tension acting on it. Thus, the angular momentum is going to be equal to, the angular momentum of mass little m is going to be conserved. Okay, so to see how we're going to use this, we're actually going to solve this tabletop problem. We'll do that in the next video, but for now, we'll see you in class. Bye-bye.